morning we'll have Shang Liu talking about shifting insulators or taking defects to the topological insulator.
Thank you for the introduction. Thanks for the opportunity to speak here. First of all, I have to apologize that this talk is not about high energy physics. Julian put me in this session only because I'm only available today. So in this talk, I'm going to talk about this work about two-dimensional rotation symmetry protected topological crystalline insulators. For most part of the talk, we'll focus on a specific model which read out the shift insulator, and in the end of the talk, we'll extend the discussion to more general settings. This work was done with Asher and Aslam. It's not the latest work, but I hope it's still interesting to some of the audience here. Here's the outline of the talk. After a brief introduction to topological crystalline insulators or TCIs, I'll focus on the main part of the talk, which is the shift insulator model. And near the end of the talk, I'll give some more general results about TCIs based on our discussion of the shift insulator model. Okay. What is a topological crystalline insulator? By definition, a TCI is a topological phase protected by crystalline symmetries such as translations and rotations, as well as the charge-1 symmetry. A very simple example is the following. So we can consider a 3D system with a single mirror reflection symmetry. By definition, when this mirror symmetry is not, if there's no such a mirror symmetry, the system should be trivial in the sense that you can adiabbatically deform the system to a trivial atomic insulator. This implies that we can, in the presence of this mirror symmetry, we can actually symmetrically trivialize the two sides of the mirror and reduce the problem to effectively to a 2D system with on which the mirror symmetry acts as an internal T2 symmetry. If this 2D system with T2 symmetry happens to be for example, if it's a T2 SPT, then this implies the original 3D system has some non-trivial topology. It can even have some gapless surface modes if this T2 SPT also have gapless edge mode. Okay. So far, the story of TCI looks very similar to ordinary internal symmetry protected SPTs. But there are some important subtleties. So here, let's make a close comparison between these two. Here I listed three equivalent characterizations of internal symmetry protected SPTs. First of all, by definition, these phases are separated from a trivial phase by gap closing. And for free-form system, these internal symmetry protected SPD phases always have symmetry protected gapless surface states, and also they have Wannier obstruction, meaning that it's not possible to have symmetric Wannier representation for the field bands of the system, also for the free-form case. So what about the crystalline symmetry case? The first condition, the first property is basically the definition I used here, but there is some important subtlety that we need to decide what we mean by the trivial phase. In the internal symmetry case, there's always a single single trivial phase which is equivalent to the atomic insulator. But in the crystalline case, it turns out that different atomic insulators can be topologically different, as you will see later in this talk. And for most part of the talk, I will regard all these atomic insulator phases to be trivial. And secondly, for crystalline symmetry protected SPTs, there's gapless surfaces is not necessarily exist. And we will see in this talk that our shift insulator model actually doesn't have any protected edge mode. The third condition, Wannier obstruction for the free-form case, I think it still holds for the crystalline case, although I don't have in my head a rigorous proof for that. Okay, now let me introduce our shift insulator model. To describe our model, I need to first review this Howden model, which is a simple model of a chain insulator. This model is a model of three spinless electrons living on two-dimensional honeycomb lattice. They are both nearest neighbor and second nearest neighbor coping. When this two-band model is half-filled, the filled band has a non-trivial Chern number, which is minus sign of lambda, where I lambda is the second nearest coping along these arrows. And our shifting to the model is very simple. It's just the stacking of two such ordered models with opposite lambda parameters, meaning they have opposite Chern numbers. We also want to impose the six-fold rotation symmetry on the system. So in order to specify such a rotation symmetry, we need to specify the orbital angular momentum for the electron orbitals in the two layers. And here we choose them for the reason that will be clear soon. We choose the orbital angular momentum for the electron orbitals to be opposite for the two layers, namely small l or minus small l. And this enters the definition of the rotation symmetry. When you do a lattice rotation, apart from moving the location of the fermion operators, you should also include the phase factor, which depends on this orbital. And for most part of the talk, we will focus on the case where it's small l equals to 1. So you can imagine we have p plus and p minus orbitals for these two layers.
Can you remind me again what you call shift symmetry?
I'll explain it. So for this model, it's easy to check that there's no symmetry protected gapless faces on the edge. And this is not surprising because this lattice rotation symmetry doesn't have a local action on the edge. So we don't expect any symmetry protection to happen. But nonetheless, this model does have a Wannier obstruction in the sense that if you check the symmetry representation of the rotation symmetry at high symmetry points in the momentum space, these representations cannot be reproduced by any atomic insulator with the same number of field bands.
That's in the bulk.
Sorry?
In the bulk, right?
Yeah. This is non-interacting signature for the non-trivial topology of the system. And the main question we want to address in this talk is that is there any other topological signature which may even survive interaction?
When I said that there's no protected gapless edge, I mean is it kind of just locally it can be gapped, but like if you have a boundary with six-fold rotation symmetry, are there still like points where you're under
It can still be gapped. So we can
everywhere?
Yeah, everywhere. We can explicitly write down some C6 symmetric term in the Hamiltonian, and then we create it on like symmetric system, open system, and we can check the edges everywhere again.
So, why do you say Wannier obstruction is non-trivial symmetry errors in case space? I thought that Wannier obstruction means that the real space statement have localized Wannier orbitals in real space.
Sorry.
Why is Wannier obstruction the statement that you have non-trivial symmetry errors in case space?
I'm not sure. Can you repeat it? Question is?
I just want you to explain the second bullet points.
Yeah, Wannier obstruction for the real space. And question?
Question is, why is that the case?
It's like so our model has two field bands, so there are not many. There are only finite number of symmetric atomic insulator which can have two field bands, and you can check the symmetry representation of our model doesn't match with any of these which means you cannot have a C6 symmetric Wannier representation.
Just to understand, is it important that it has only two bands in that statement? Like if you add more bands?
Yeah, that will probably be different. Our model does have two bands. So it's like you have two electrons in each of these. the main question we want to address in this work is whether there are other topological signature which can survive interaction and show that this model is topologically non-trivial. To answer this question, it's useful to consider this a simple thought experiment. So we imagine we thread some magnetic flux perpendicular to the system, and let's see what's happening. Because we have chosen a positive number for the two layers, so this flux it doesn't induce any charge response. But since we also choose the orbital angular momentum parameters for this layer to be opposite, so at least intuitively, this flux should be able to trap some angular momentum. So there should be some angular momentum pumping due to this flux. Although this intuitive picture turns out to be not quantitatively correct, but let's just intuitively speculate such a response exists. And to describe such a response, we can write down such a effective action, which is a mutual Chern-Simons term between this electromagnetic probe field and another probe field omega, which couples to which is some U1 field coupling to the charge of the six-fold rotation symmetry. We assume I'll address this in a moment. Here we assume that in some low energy continuum theory, this rotation symmetry is somehow promoted to some U1 symmetry and can be coupled to some U1 probe field, which we call so if you differentiate this action with respect to A, it tells you that the flux of this magnetic field, the flux of A will trap some charge of omega, which is.
So is it omega equivalent to the discrete version of the spin connection?
Yes, I'll just describe this in the next slide.
But if it is discrete, how can you guarantee the when Z coefficient is quantized? Because when you have full rotation symmetry, then if you have the homomorphism invariance, the when Z coefficient must be quantized for gap system. But if you just have discrete rotation, how do you
Can you speak louder? Excuse me, sorry.
So is there any structure which guarantee the level quantization of this when Z response?
It should be quantized. This omega very much behaves like just a U1 So there should be some quantization.
Why there should be? Because for the usual U1 rotation, it's guaranteed by the diffeomorphism invariance, then it should be quantized. But here you don't have diffeomorphism invariance.
There should still be some discrete pH symmetry that is expected. It's probably sufficient.
Yeah, it's like it remains quantized but becomes periodic.
No, I see.
Like when you break U1 down to Zn.
But here, I simply assume there exists some U1 field which emerges in some low energy. So this action tells us that there's actually another related topological response in the system, which is if you thread the flux of this omega field, whatever it is, it should trap some electric charge. So based on these arguments, we propose these two topological responses for our system. The first is if you create a disclination, which is a defect of the rotation symmetry, then there should be some charge bonding to it. And on the other hand, due to this first argument, if you suppose we put the system on let's say on a torus, you thread a monopole flux, then there should be some sense of angular momentum pumping due to this monopole flux. And so before talking about these two concrete responses, we first need to address whether this omega field, whether it exists or not. It's actually already discussed in an old paper by Xiaogang and Zi in 1992. So it turns out that omega field is nothing but just a connection one form of both the space manifold. So it is some U1 probe field. And in this paper, they show that for a quantum Hall fluid, if you have such a mutual Chern-Simons term between A and B omega, then it tells you that the total number of flux quantum in the magnetic flux quantum in the system is proportional to the total number of electrons up to some universal constant, which they call the shift. And this shift is proportional to the coefficient of this mutual Chern-Simons term and also the number of curvature quantum in the total number of curvature quantum in the system, which is a purely topological quantity.
Sorry, is mu quantized or not?
Mu should be quantized.
Is mu
Yeah, in their paper they mu should be quantized. I think that's it. Both A and omega are U1 field if you use a UR. There's also some, in this paper, there's also some quantization of the so-called spin vector, which is related to this mu, but not directly this one. So as an example, if you consider the lowest Landau level of spinless electrons, then this mu is actually 1/2, and this shift equals to 1. This is I'm not pretty sure about the quantization.
It is quantized, but may not be as integer. This is like coefficient of Chern-Simons term, which roughly like any real number, but for the compact theory, it has to be some rational number.
Maybe like some type of a hidden fraction, like
For the non-interacting theory, maybe there is an integer quantization, but for general interacting theory, it can be rational number.
Okay. So now let's turn to the discussion of the topological responses. The first one I want to talk about is the disclination charge. So as I said, the disclinations are defects or the flux of the rotation symmetry. So on the honeycomb lattice, the disclination can be simply made by just choose the rotation center and remove the field 60-degree edges, and then you glue the open edges. This creates some 6 minus n-gon placket, as in these two examples. And we expect this disclination to trap some magnetic charge. And there's also a clear correspondence between these disclinations and the curvature of the space manifold. So if you put several such disclinations on a closed manifold, and if you count the Euler characteristic, you derive a relation like this, where this big n sub small n is the number of 6 minus n-gon disclinations on the system. And this tells us that where this n sub r is the number of curvature points. And this tells us that each 6 minus n-gon disclination corresponds to n divided by 6 curvature point. Okay. And here's the result. For the shifting star model, we check that indeed there's some charge trapped in this disclination. And this result is obtained both directly and analytically. For example, if you take a pentagon disclination, and you take these parameters for the model, this disclination charge modulo integer is 1/6. You can see from this formula these disclination charge for different parameters of the system are always some very nice fractional numbers. This is not a coincidence. And actually, these disclination charge are guaranteed to be quantized. This is because essentially you can put several disclinations on a closed manifold, and the total number of electrons in the closed manifold must be integer. And from different such disclination configurations, you can derive various quantization rules for the disclination charge. And in particular, one can prove that the disclination charge must be an integer multiple of 1/12 for any disclination. And this quantization rule implies that discrete charge is topologically stable, meaning that the discrete charge module integer is topologically stable, meaning that if you continuously tune the Hamiltonian without closing the bulk gap, then this quantity just cannot change. And we will see later that the discrete charge response for the shift insulator cannot be reproduced by any atomic insulator with the same number of electrons in the unit cell. Therefore, this is a signature proving that the shift insulator has functional topology protected by the C6 symmetry. Actually, also the translation symmetry. You need a translation symmetry to make this compact. That's a close random construction.
Can you really get 1/12?
For Haldane model, yes, but for shift insulator, you only get 1/6.
What do you mean for Haldane model? For the chiral model?
Yeah, for that you can also make disclination and parity chart. For that you get 1/12. Now is a good time to revisit this effective Chern-Simons action we read down at the beginning. Let's call the coefficient this capital S. By differentiating the action with respect to A, we can obtain this formula for the disclination charge, which is proportional to this coefficient S. And from the formula, from the disclination charge formula of the previous slides, we can fix this coupling of the mutual Chern-Simons term, which can then be used to predict the other topological response. Namely, if you thread a flux in the system, the charge of the omega field must be S times the number of magnetic flux formed. To check this second response, we put the system on a C6 symmetric torus and then thread a monopole flux. A C6 symmetric torus is just you can take a big hexagon and identify the opposite edges. And to create a monopole flux on the system, the strategy we do is we pick some rotation center and imagine threading the total flux phi into the torus and then spread it out uniformly on the whole surface. When this phi becomes quantized, these electrons won't see the flux injection to effectively get some monopole flux. But also, when phi is not quantized, although it's not a monopole flux, it gives us a natural way to interpolate between different monopole charges. And here, this field converter is C6 symmetric, so we can write down some C6 symmetric gauge for this field configuration. And under that C6 symmetric gauge, we can just define the C6 rotation symmetry in the Euro way. And once the rotation symmetry is defined, we can measure the angular momentum of the many body ground state of the system modulo 6. And we just propose that the charge of the omega should be the change of the ground state angular momentum due to the presence of this monopole flux. And we found that in the presence of a quantized monopole flux, the ground state angular momentum changes by this quantity, which is precisely what we expect from the effective action from the last slide. And here you may wonder if the system is always gapped, how could the many-body ground state has different? How could the angular momentum for the many-body ground state change? And it turns out that if you look at the spectrum with respect to this flux injection, when the flux is quantized, it's true that the system is always clearly gapped. But when this phi is in between, there's some states transporting between the lower and upper gap, and these are precisely responsible for the change of the ground state. It's nothing but the quantum Hall effect. Okay. So we wanna.
Sorry, total flux must be quantized on the torus.
Yeah, this is like when I say phi is not quantized, it's not a monopole flux. We are threading some flux phi here. First, inject some flux into the torus and then spread it out uniformly. So when this phi is quantized, that's the monopole flux. But when phi is not quantized, it's not a monopole. Just
I see. It's like the net flux is actually 0. Is that?
yeah, exactly. That's a convenient way to interpolate between different fluxes. We're going to compare our shifting to the model with atomic insulators. So let's give we need to do let me give a brief discussion of C6 symmetric atomic insulators. Atomic insulator can have orbitals at different sites, different locations in the real space, and in the presence of C6 symmetry, we can classify these different orbitals according to their little groups. For example, there can be C6 symmetric orbitals at the honeycomb plaque center, which we call A-type orbitals. There are also there can be C3 symmetric B-type orbital at honeycomb sites, and also C2 symmetric C-type orbital at honeycomb bonds, and there can also be generic orbitals whose little group is triple. And we show in our paper that the topological response of these atomic insulators actually only depends on the number of A-type orbital in each unit cell, and are given by this formula. This result gives us two pieces of information. First of all, this proves that there are actually many distinct atomic insulators in the presence of C6 symmetry, because they can have different topological responses depending on how many A-type orbitals they have. And moreover, our shifting model is actually not equivalent to any of these atomic insulators. This is because if you want to have two bands, the only possible choice is either you have two A-type orbital or one B-type orbital in each unit cell. But neither of these two cases can reproduce the topological response for the shifting insulator. So, which proves that the shifting insulator is not atomic. And in the paper, I can show that there is a D12 classification for the shifting insulator model, which means if you stack 12 copies of this model, then this whole thing becomes true.
Question: if you don't care about the number of bands, then you can get the right response from the.
Yeah.
Well, the number of bands is also filling, so it means that it's still a different phase than imminence. You have more charge per unit cell.
There's lots of core electrons that no one ever thinks about, right? And there are lots of S-field bands around, so
Yes.
it's not. I think it's reasonable to ask if you have a lot of inert bands around. How does this change? I think isn't that this stuff? That's why this is fragile topology. Is that so you can get the same response from an atomic insulator with more numbers.
So if you restrict the number of electrons in each unit cell, then it's not equivalent to any atomic. Okay. So as you mentioned, we also found that this system actually has fragile topology, meaning that although the shifting intermodal itself is not equivalent to an atomic insulator, but if you are allowed to stack only some other atomic insulator, then this whole thing becomes Schematically, you have such an equation. If you imagine you move this part of this term, this is some atomic insulator. If you move this term to the right hand side of the equation, you effectively have some atomic representation for the shifting insulator, but with negative coefficients. And you can even use this representation to reproduce the topological responses using this. These are all I want to say about the about the shifting model. We also have some, in the paper, also have some more general results about TCIs. But due to time constraint, let me just highlight the results without going into the details. So based on some arguments, we argued that we conjecture that any point group protected TCIs, which do not have any protected gapless states, must be either atomic or fragile. Our shifting model is just an example of this. And also, in our paper, based on the dimension reduction procedure, we give a classification of 2D PCIs protected by rotation symmetry, both for the free ferment case and for the reduction and retraction. That's all I want to say. Maybe skip to some.
Any questions?
So, given that this is fragile, like, I don't know, how would you hope to see this? Like, what are you supposed to look for, given that this is so sensitive to the fact that only when you restrict it to given filling per unit cell can you distinguish between these different types of insulators?
Sorry, I understand.
How do you observe a fragile topological insulator?
You mean experimentally observe or?
Yes.
Well, the charge of the disclination is not fragile. It's just you don't have an atom there, so it's not atomic.
No, but I mean, I don't know. So that it's only a fraction. I mean, the 12 copies presumably comes from, you said it was a 12, so if you put 12 of them on top, it becomes an integer.
There could be an atomic realization of the same phase where you have like a triangular lattice and you're doing an on-site rotation. It would have the same physics of like a charge trapped at a disclination. You still have this order 12 classification, but it would be atomic. Maybe you can answer better.
You can't really distinguish between atomic and fragile experimentally because of the reasons you described, but that's not a deal breaker in the sense that even atomic phases can have non-trivial responses. And that you can hope to see.
Well, it's just that even if atomic, what you call trivial themselves have non-trivial disclination charges, it's just what you use to tell these things apart. Right? You put a disclination in, it'll usually bind some charge, anything. So you cut up a chain, there'll be extra charge in the chain.
Right.
Usually.
Fractional lines important.
What's that?
Fractional lines important.
It's okay.
More questions?
So what are the part you skip? Is something you want to expect?
I did actually skip. Maybe this picture is just it's an argument for this conjecture. It's not a universe. Basically, it's saying that if you have using the dimension reduction procedure, you have if you have a point group protected TCI without any edge group, then you can basically reduce dimension reduce the system all the way down to zero system. You may say maybe this implies this whole system is just equivalent to the stacking. Okay, if you try to restore the translation symmetry, you take many copies to the system. But this doesn't imply the whole system is equivalent to such a common insulator, because this identification already has some. It's not a one-to-one correspondence, because when you do this dimension reduction, you're allowed to symmetrically bring in some other stuff, which I think people point out it's a joining procedure. So, and this procedure of adding extra stuff is nothing but like stacking some other components into the system. So, based on this observation, any such TCI should be either atomic. But it is not. That's a very handy value.
Okay, if there are no more questions, thanks. We'll be back at 2:30.
Not from stairs.